Hi everyone, good morning, good afternoon. My name is Jaap Nienhuis. I'm from Utrecht University. I'll be talking about river delta modeling. First of all, thank you so much to Chris Hein and the rest of the IGCP crew for putting together this webinar Geocron series, to my sponsors NWO and NSF for sponsoring this work, and to my dear colleagues, friends, and students who have been instrumental in putting this together. So I'll be talking about river delta modeling, and I don't need to tell many of you that one of the most fascinating things about river deltas is that many of the world's current problems, environmental problems, come together in deltas. Deltas are faced with sediment shortages from river dams, sea level rise, other aspects of global warming that threatens delta size and impacts delta flooding. And there's a lot of engineering works that occurs on delta plains. And on top of all of that, river deltas also see a lot of very cool, interesting, and rapid autogenic dynamics. So this is an example, the Sitting River in Myanmar, where you see a tremendous morphodynamic, morphologic variability over this time lapse, which loops through about 30 years of delta or estuary change. So how on earth should we go and use models to understand what's going on, right? This is very difficult. There are a lot of things happening at the same time, a lot of boundary conditions that are changing as we speak. What kind of metrics do we extract from something like that to run our models, but also to test our models? That's what I'll be talking about. To illustrate that, first I'd like to explain kind of what I call the one delta approach. So if you would do this and test your model and run your model to simulate one specific delta, what you do, of course, is you have a model that I'm illustrating here on the right. It's a shoreline model that I've been using before to, for example, study how channels orient themselves on wave influence delta. So you see an example wave influence deltas on the bottom right, the Ombrone, and a model simulation on the top. Right, in order to learn something about deltas and perhaps make projections of delta change into the future, you need a numerical model. From that model, you need to extract, here, let me use my pointer. You need to extract some metrics that you will use to compare this to real world deltas. Then, of course, with those metrics, you can start validating, but also importantly, calibrating your model and some of your model parameters. And you use that to then understand both when it works, so what kind of parameters are likely operating at this delta, but also to understand the misfits. So where does the model fail? And in that loop, again, you can adjust your numerical model and repeat this exercise. And hopefully, when this works out, you are able to project forward and perhaps assess delta change. However, one of the difficulties of this one delta approach is that, of course, you have many model parameters in morphodynamic models, many parameters that are going to be very poorly constrained. You have morphodynamic spin-up, which is a term we use just to illustrate that models have their own reality, and sometimes it takes a while before a model gets to equilibrium, and that might be very different from the equilibrium that you observe in nature. But most importantly, for this one delta approach, the validation is going to be very difficult. First of all, because you don't have that much field data to compare it to. You have one delta. Morphodynamic change can be very slow, so you oftentimes don't have long time series of delta change. But you also have a very narrow bandwidth for calibration. Right? You compare just this one delta to this one simulation, to a suite of simulations, but you can only test it for this, in this case, one set of channel orientation data. So I'd like to compare this in this talk to something that I've been using a lot, which I call the many delta approach. So rather than, and the difference is in this box here, right? We don't validate then against one single delta, but across many different deltas. And that has some advantages, right? So here I'm showing the same again, but then you can compare it not just to the Ombrone delta here, but for example, also to this other delta, the Sao Francisco. And of course, with that, you have more data for comparison, but more importantly, you have a wider bandwidth for parameter testing. So you don't only test this specific channel orientation here, but you can say, well, what if I model a different channel orientation? Does it then work to simulate this other delta? So you have a much broader range in parameters and also in outcomes that you can test in your model. But importantly, it does require something, of course, and that is more data, but it also requires you to think a bit more about what type of metrics you use to compare your model to your field data. So for example, with this model, this is a paper from 2016, EPSL from my PhD time, which I thought was appropriate in this context of this methodological talk. You can run, if you're interested in delta channel orientations, right, and you have this model, you can simulate delta channel orientations for wave influence deltas. You can run this model for increasing amounts of fluvial sediment supply. You can model it for changing what we call a bypassing fraction, so how much of the alongshore sediment transport is able to bypass the river mouth and make its way to the other side of the river mouth. If you have a very strong river mouth jet, for example, you can block a lot of it and you end up with a very small bypassing fraction. So this is a very important fraction we found out to change the channel orientation of deltas. Right, so back to this, again, this many delta approach, you can run this simulation for many different input conditions to then simulate different channel orientations in deltas. But just to compare this to real-world deltas is still very difficult because, of course, you can imagine it's not just fluvial sediment supply, but it's also many other things that vary between deltas, right? You have wave climates that vary. You have grain sizes that vary. You can have slopes, offshore slopes that vary, and they all might influence the delta channel orientation. So in order to do that comparison appropriately, you need to really dive into what the model is doing and understand why, and this is a simple model so we can do that, but really understand why for these different conditions you have this amount of channel orientation. So the second step, extracting non-dimensional metrics and thinking about non-dimensional metrics, becomes increasingly important across many deltas. So this is a complicated figure, not to dive into it too deeply, but just to illustrate that in this case we were able to tease apart for all of these three different types that we have in terms of channel orientation. So kind of a non-affected channel that just goes straight into the ocean, or a downdrift deflected channel to the right, in this case away from where the waves come from, or an updrift migrating channel that migrates updrift into the direction of the waves. And in all of these three cases, we're able to analyze the alongshore sediment transfer patterns and really find out what it is that makes channels orient in a specific way. Right, and with that, we can then construct non-dimensional metrics. So in this case, we defined an updrift migration index and a downdrift migration index that captures the wide variety of orientation types that we see along natural deltas. In this case, model deltas, I'm sorry. For these red ones, you have a lot of downdrift deflected channels, and in this blue regime, you have a lot of updrift migrating deltas. I don't want to go too deeply into why this is. If you're interested, please come talk to me or read the paper. The important thing is, what I want to discuss is that with this non-dimensional framework, you can then go back to individual deltas and really test these model outcomes by comparing them against natural examples here for about 10-15 different deltas. Right, the Barham, San Francisco, St. George, Coco, we all have a very different channel orientation, and as you can see, it nicely aligns to to the field in this to the model in this non-dimensional framework. So this is that loop from numerical model to understanding deltas that I've talked about. And then, of course, with this model, if you have some confidence, you can then project forward and say, well, what if, for example, fluvial sediment supply is changing in time? And then you can play these fun little delta games where you see under low supply conditions, you have a downdrift deflected channel. And then when you have, for example, land clearing in your drainage basin, you increase sediment supply, and you might be able to reorient your wave influence delta channel and then move it toward the direction of wave approach. So then you can really talk about delta projections and changing boundary conditions and how that then affects deltas with this very simple delta data model comparison. What I just showed you before was a very simplified model, a one-line shoreline model, but of course you can do this with more complicated models too, where you don't necessarily understand already the type of physics that are likely going to be important, but rather want to explore a wide range of different processes in a single model. And what I'm showing you here is a model output time lapse where we try to get at this bypassing fraction. So without having to assign it a priori, really look into river mouth morphodynamics to extract what type of bypassing fraction arises autogenically from this model simulation. So this is del3D simulation where you can do that. But then again, make that same data model comparison and go through this step approach again with, in this case, different types of metrics and different types of field cases, perhaps. What I also wanted to talk about is a second project where we do this, but then on a much bigger scale and much longer time scales. May be interesting to some of you too, and that's thinking about sea level changes in delta. So, of course, we know sea level changes are happening and have happened a lot in the past, but how do they affect river deltas? Can we use this same model data approach to perhaps say something about the risks of sea level changes on deltas? What we did in this case, of course, is we followed these same 5 steps from numerical model, from extracting metrics, validating them against many deltas, using that to understand what is driving delta change, and then use that to project forward what is happening across many deltas. And we used a very simple model, nicely illustrated by this movie from Anderson et al. 2019, where you see this blue shade here is sea level that moves up and down on glacial timescales. And you see here all of these colors are different delta snapshots in time. So during a transgression regression, it draws a new color. So you can nicely see this delta develop over time, where the size of the delta and the shoreline transgression erosion, so transgression regression, is strongly affected by sea level cycles. And this is a very simple model, but we can, I think, use that very effectively to say something about what's happening in modern deltas by comparing this against our observations. There's, of course, several ways to go about this comparison. One is where you look into time series, right? Because for some deltas, for these long time scales, we have good time series. And this is what I'm showing you here is global mean sea level change in millimeters per year throughout the Holocene. So if we're going from very fast rates at the end of the glacial all the way to very small rates right now. And we can put that against our data for shoreline trajectories, and we see that in general they responded to this decrease in sea level changes, where we first have a period of transgression, right, a retreat of the delta shoreline over time. And when sea levels fell to below about 5 millimeters per year, we found that the deltas grew over time. And this is from reconstructions paleogeographic reconstructions for all of these different deltas. So we can test a model using time series like that. And we have a project underway where we start to do this, but in this case, I don't have results yet, so I wanted to talk about something similar. And that is not testing against time series of delta change, but rather at the broad range of observed delta change that we get from remote sensing that we can very easily extract from deltas. So this is an example remote sensing image where blue is all the land loss of the Mississippi Birdfoot Delta and green is land gain. So we can sum that all up and say, well, this delta on average lost or gained this many square kilometers each year. In this case for the satellite record, so about the past 30 years or so. And you see quite a range. There's some deltas, the Ganges Brahmaputra grew a lot, other deltas like Mississippi, or some deltas in Indonesia have shrunk over the past 30 years. We can use that to train our model, right? Now we have a very broad set of outcomes we can compare our delta to our model to. And so this model in this case is very simple. Very simple morphodynamic model where we simplify a delta by saying it's a triangle, more or less, fed by sediment supply and is able to move the shoreline outward, so regression or inland transgression over time, dictated by sediment supply, but also, of course, by relative sea level rise. And we have these triangles for many deltas across the world. So what we can then do is use this model to make delta projections, predictions for all deltas for the past 30 years and compare it against observations of deltas. And when we do that, we find this trend here. So every dot is an individual delta. We made this comparison for thousands of different deltas across the world. And we see that it works in some cases, and clearly it doesn't work in all cases. We end up with an R squared, so variance explained of about 40%. So still a lot is unexplained, but there is enough explained and there's no great bias that we detect in our model, that we have enough faith to make projections. But note, of course, that these projections are very uncertain, and you can see that based on this, of course, we can calculate the error in our projections globally, but also for individual deltas. So we can sum them all up and say, well, in our observations from the remote sensing that I showed you, we find gradual delta land gain over time, approaching almost 650,000 square kilometers for all deltas globally, but under different sea level rise climate scenarios. We will have reductions ranging from very slight reductions under optimistic CO2 emissions to very drastic reductions of delta extent under very high sea level rise scenarios. And we make these projections globally. We can make these projections for individual deltas, but as I said, they're quite uncertain. But you can see broadly that there's still a mixed picture in delta land gain, land loss under 2.6, but under 8.5, most deltas around the world will be losing land rapidly. And with that, I hope I've illustrated to you some of the tools we've used to, some of the steps we've used in our lab to compare delta models against observations for a lot of deltas at the same time. And just to repeat, we do that because we get a much wider set of parameters that we can test against models, so we can much more effectively test our model, and we can be much more certain about model outputs. Okay, so thank you so much, and I'm looking forward to the other presentations in this series.